Welcome back. This video is on two really special expansions. Okay, and these get used heaps. It's really well worth recognizing what happens in these particular patterns. And the first one that I'm going to talk about is the difference of perfect squares, and this comes up all the time. Okay, so get used to this. Difference of perfect squares, also known as DOPS. Okay, in your textbook it'll be called also difference of two squares, so DOTS, but I've always known it as DOPS, so there you go. Let's just have a look at this. Let's expand this: x plus 6, x minus 6. Okay, let's just expand this out quickly. X times x is x squared. X times negative 6 is negative 6x. Positive 6 times x is positive 6x. And positive 6 times negative 6 is negative 36. Right, so now that we've done that, what's negative 6x plus 6x? That just cancels out to 0, and you get x squared minus 36. Okay, let's just try another one. X plus 10, x minus 10. Let's see if you can get the pattern. X times x is x squared. X times negative 10 is negative 10x. Positive 10 times x is positive 10x. And positive 10 times negative 10 is negative 100. If we simplify that, again we're going to get negative 10x, positive 10x. They cancel out, and you just get x squared minus 100. So let's just have a look at these two examples. We could keep going and doing millions of them. But what is the connection between that and the final answer of that? Okay, have a look, see what you think. Similarly, what is the connection between this here and this here? It's expansion. Okay, so what we get, let's have a look at this. I'll just write it down. If you have x plus some letter a, and you multiply that by x minus a, what do you get? You get x squared. Now what's happened here? Between the, we've got 6's here, and we end up with 36 over here. We've got 10's here, and we end up with 100 over here. And it's always minus, you see here. If we did more examples, you'd see. So it's actually minus a squared. And this is actually the difference of perfect square rule, otherwise known as DOPS. Okay, why is it called that? Because you've got the difference of perfect squares here. You've got a perfect square here, x, a perfect square here, a squared, and the negative is the difference. So you've got the difference of perfect squares, the difference, one perfect squared minus another perfect squared. Okay, and this is the expansion that you'll always get. Okay, and so this is a super important result, and let's just blitz into some examples. So let's do an example. Just quickly expand x plus 7, x minus 7. Now you see you've got x plus something, x minus something, so you should recognize this as the difference of perfect squares. And what it's going to be is going to be equal to the first term squared, x squared, minus the second term squared, minus 7 squared. Okay, that's due to DOPS, which is equal to x squared, that's a squared, minus 49. And that's it. It's just a fast way to expand, and you'll see later it's a fast way to factorize. Okay, stuff like that. Okay, so x plus 2, x minus 2 will be equal to the first term squared, which is x squared, minus the second term squared, which is 2 squared, which is equal to x squared minus 4. And there you go. So it's a beautiful little thing where you can just quickly get the solutions out. 2x plus 1 times 2x minus 1. Let's just think of this. What have we got here? It's the first term, so 2x squared, minus the second term squared, so minus 1 squared. That's what it will turn out to be, which is equal to, just get this right, what's 2x squared? This means 2x times by 2x. 2x times 2x is 4x squared. Minus 1 squared, which is minus 1. Okay? And that basically is DOPS, and it's a lovely, lovely, lovely little thing. Okay? You might think I like that a little too much, and you'll see it often helps us. Our last, must be late in these perfect squares. So let's go and have a look at perfect squares expansion. Okay, again, let's just do some examples. What's x plus 3 squared equal to? Well, that's x plus 3 times x plus 3. Let's expand that out. We've got x times x, which is x squared, plus 3x, plus 3x, plus 9. I'll just squeeze it in here. Which is equal to, if you collect like terms, you've got x squared, you've got plus 3x, which is plus 6x, plus 9. Can you see a pattern between this and this? Let's do another one. I'll start a bit over here. X plus 7 squared is equal to x plus 7, which is x squared plus 7x plus 7x plus 49. If we simplify that, we get x squared, 7x plus 7x is 14x plus 49. Okay, let's just have a look at what is the connection between this and this. What's the connection between this and this? I wonder if you can see the difference. Okay, let's see what it is. In general, if you have x plus a and you square it, what you get is this. You get x squared out the front. Okay, whatever the first term is squared. In the middle, can you see how this is x plus 3 and you end up with a 6x there? Here you've got x plus 7 and you end up with a 14. In other words, all it does is you end up with twice whatever a is. Okay, so twice ax. Say that again. Here a was equal to 3 and you ended up with twice 3, which is 6x. Here you started with 7, a is equal to 7, so you double 7, you get 14, 14x, and so we get plus 2ax. And what's the term on the end? We just add a squared, whatever that last term is. Okay, so that is your perfect squared expansion. And similarly, if we've got x minus a all squared, that's equal to x squared minus 2ax plus a squared. So please note the difference between those two, but these are your perfect square expansions. Okay, perfect squares. Remember that perfect squares means just something times itself. So there we go. Let's go and do some examples of this. Example. Okay, expand x plus, what haven't we done? 5 squared. Okay, so what we do is we square the first term. We've got this x squared. I'll leave the middle term, I'll come back to that, but 5 squared, positive 5 squared is plus 25, because that's 5 squared, 5 times 5. What's the middle term? Well, the middle term is you just times the two terms together. So x times 5 is 5x, and then you double it. Double 5x is plus 10x, and that's your answer. I'll just do a bunch of these, hopefully you can follow. X plus 9 squared. I wonder if you can figure it out. X, you do the first term squared, you do the last term squared, plus 81. In between, you look at the two terms. Here we've got x, here we've got positive 9. What's x times positive 9? You get positive 9x. Positive 9x times 2 is positive 18x. And that's your answer. Okay, I'll just smash out a couple because it takes a while sometimes to see this pattern. X minus 1 squared. Okay, again, write the first term squared, x squared. Write the second term squared. Negative 1 squared is positive 1. Negative 1 times negative 1. What's the one in between? X times negative 1. X times negative 1 is negative 1x. What's negative 1x times 2 is negative 2x. Okay, so you get really, really good at this the more you do. Okay, another example, and I might make this my last example. Okay, let's do 2x minus, I don't know, 7, 8, 9, what haven't we done? Let's do an 11 or something like that. Okay, and I'm just going to be a bit more careful here. Again, oops, better square it. First term squared. What's 2x squared? 2x squared is 2x times 2x is 4x squared. Be careful there. The last term squared is negative 11 squared, which will be positive 121. Okay, let's think about what's on the inside. Look at your two terms. You've got a 2x and you've got a negative 11. Let's multiply those two together. 2x times negative 11 is negative 22x. Just write that there, negative 22x if you multiply them together. And then we need to multiply them by 2 to get the term that's inside. And so you get negative 44x, and that's your answer. Okay, get some practice with those. They can be tricky, but if you get them, it saves you heaps of time later on in your math.